Class, this is week 8 Wednesday lecture, starting on chapter 6, structural analysis, and we'll be covering two topics, trusses and frame. Today we'll get through at least one example of a truss structure in the solution feature. A little show and tell, difference between a truss and a frame. I have a truss system. I'm going to consider it bolted. I've got wing nuts on here, and it's a very stable structure. I can't move it. Loads anywhere. I can't move it. This frame can be loaded anywhere on the structure. Concentrated loads, uniform loads, combination. It could be loaded in any direction. Uniform. Doesn't matter. This is going to work very efficiently. And you can build this frame by repeating whatever the structure is. In this case, this is a square. Some other configuration, it doesn't really matter. That is the basis for a frame. And again, the key is you can load this anywhere. When that happens, you're going to get deflections in these members. And for design, you have to go to what we talk about in strength of materials. Bending stresses will develop, and other internal stresses will develop in the bend. But design is going to be a little bit more sophisticated than when we work with trusses. Just give me a few seconds, well, probably more than a few seconds. I'm going to take the wing nuts off so there won't be bolted connections on this. Takes a while to get the wing nuts unfastened. I don't want to find all over the place. That one just did. Stay with me. Maybe a truss. Connection to finish. So what I've done is I've taken the bolted connections off. And this is what I have. Absolutely no load bearing capability. What I'm going to do is add a diagonal member to this. It's a little tricky because it has been crafted precision so that all the members fit together. So what I need to do is make sure it's actually fix these at the same time, or there's no slack if you do it. Stand up and make it a little bit easier. Let's see where I'm at. Okay. So what I've done is I've added a diagonal member. There's no bolts back here. There's no wing nuts. There's nothing to fasten it. Look at this. A lot of pressure. It's very stable. It carries load very efficiently. Get a lot of bridge decks, truss structures. That's one you can see in Oklahoma City is at 235 between Interstate 40 and Interstate 44. It's that railroad bridge. That bridge was actually constructed off-site, brought there, and then one evening they closed state down, simply move that bridge in place and do all the attachments to the structure. It's a truss. We can expand this truss by repeating the shape as far as we want to go. And it's very efficient load carrying. It's an important consideration for trusses. Whereas in the frame you could load anywhere, trusses you can only load at these joints. I also call these pins. Basically, these are frictionless pins. They're not bolted, they're frictionless pins. So we have this structure, we can put a load in direction, but it has to be loaded at joint. And what that does is it assures you that each member is going to be either pure tension or pure compression. Very, very simple to design, tension or compression. There's no bending. And again, this is something I asked on the exam. Was a truss loaded? Loaded only at the joints. That assures us that we get tension, compression in the members, nothing else. And that's extremely important to remember. If I load it over here, I'm going to suspect that we may get compression in here. If I load it over here, it's probably going to be tension. So when we give the answers, part of the value, the magnitude of the force, we need to designate tension or compression. And the reason for that, that if it's a compression member, there's a tendency for it to act like a column, which means it could be subjected to bending. And so what we might do then to counteract that is to make the member a little bit larger. Particularly what that does is it uses a larger cross-sectional area to counteract any potential bending. And the only way we know that that may be a possibility is if we know tension or compression in the member. Okay. It's a truss, very, very efficient. Talk about real C trusses, and everyone has seen trusses. Talk about that. Okay. I'm going to share. I'm going to share the notes. These are posted on Canvas. I have the notes posted on Canvas. We're talking about a truss and a frame. And a simple truss is a structure that behaves with straight uniform members arranged in a series of joining triangles and fastened at the ends form joints. The joints can be pinned, welded, riveted, bolted in the field. We do the analysis, we just assume they're frictionless pins. There's other things that can happen with these types of connections. So we assume frictionless pins doesn't affect anything in terms of determining the forces and determining the design that we could take a look at. To support stationary loads, moving loads. An example are bridge decks. And the question may be, well, how in the world you have cars and you have pavement over a truss system, are the loads transmitted to the joints only and not the rest of the structure? I'll show you that once we get into a bit more into truss and truss design. Supports basically bridges, buildings, or systems. You'll see a lot of the towers, transmission towers, have some form of truss system in there, very common. So we have three assumptions. First of all, the bars are connected at joints with frictionless pins. We assume it's that kind of behavior, frictionless pins. So we don't, very simple. What this allows us to do is go back to chapter 3 and look at particle equilibrium. What we're going to do in solving simply particle problems. First problem we ever did. All forces are applied at the joint. You need to know this. And this assures us that we have tension or compression only in the member, nothing else. No bending stresses or other stresses develop. Pure tension or pure compression if the forces are applied at the joint. For assumption, all members, joints, loads act in a plane. So we're dealing with planar statics. And here is the simple part of this. Two equations are sum of forces in the x equals 0, sum of forces in the y equal to 0. That's it. That's all we need to solve systems. And no multiplication, you're adding and subtracting forces. Again, as part of the magnitude of the force, you need to designate tension or compression. I can tell you as you're working a truss, and I couldn't do this on many of the trusses we're looking at, I don't know what members may be tension, or particularly I don't know what members may be compression. Okay, so to simplify things, you're not trying to do that. I mean, there's some problems I couldn't do, whether it's tension or compression. As we work through the problems, assume all forces are in tension. You get a negative answer, and it's compression. And this is probably the most important concept we're going to talk about in this lecture, keeping track of the compression member. If you don't, you miss something right at the very beginning, everything else in the truss is going to be wrong. And I will explain this when we get into the exam. I'm going to come back to this next topic, zero force members, once we talk about so design assumptions. Sort of repeat myself, but I want to really focus on the fact these are design assumptions. All loads are applied at the joints, and usually we neglect the weight of the member. And all the problems that we're going to look at, we do. We don't consider the weight of the member in a particular solution. And when we do this, applied at the joints, it results in tension or compression in the members. And we're going to assume that they're joined at the connections, at the joints, smooth pins. And as we work this, you can call it joint A. I probably call it pin A. It doesn't matter what you call it. Either one is going to be just fine. For design, we want to determine the force in the member, if it's tension or compression. I told you the significance of compression. It can act like a column bending. And if it's compression, what we'd probably do is design this member a little bit larger than the tension members. We know how much larger it would have to be, and that would prevent the possibility of bending stresses. Don't want that to happen. Simple truss. You can build a simple truss by simply feeding the shape, the triangular shapes. In other words, you can take this truss, there are 2 bays, and you can make this as long as you want, simply repeating this triangular pattern, and the patterns can be very different in the trusses. There are 2 solution methods that we're going to talk about. The first one that we're going to look at is called the method of joints. And the theory on this is that each joint is in equilibrium if the truss is in equilibrium. So we assume the truss is in equilibrium. It means each joint is in equilibrium. What we do then is we take the joint out. It's a free body diagram. The joint is a point. So it's a particle equilibrium problem. Do sum of forces in the x and sum of forces in the y. Okay, particle equilibrium. This is the first problem that we did. You're going to start with a joint with a known force, and usually this is going to be at one of the support joints, one of the supports. It starts with, show you how it does. So you'll start definitely with a point that has a force in it, and the supports will always have a force. So you can assume tension or compression by inspection. That is difficult, and I wouldn't allow myself to do that either. So my suggestion is that you start off at each joint with all forces are tension. If answer comes out negative, then it's not tension, it's compression, and you need to keep track of compression. Start this. This is the most important subject we're talking to today. Got to keep track of compression, and show you this in example. If you miss compression, carrying it on, if you carry it on as tension, everything that you do that point on is going to be wrong. Okay, let's take a look at a problem. This is an example truss, and what I want you to do at this particular point is ignore these numbers here. These are actually your answers that you get, and so what I want you to do is you solve a truss, put your answers in, magnitude and tension and compression. You don't have to put the units. We know what the units are. Okay, so these are the answers to the truss. We put these on as we solve numbers as we go through the truss. Okay. So this is a 3-bay. This is a bay. This is a bay. This is a bay. Each of the bays are 3 meters. I could have mentioned this 3, 3, 3. Suppose this thing had 10 more bays, doing 3, 3, 3. That's ridiculous. I mean, it's real cluttered, and the easier way to do that, and it's using this notation. This says, what this says is 3 at 3 meters. This means there are three bays. Each bay is 3 meters. So this is 3, this is 3, and this is 3. If there were 10 bays, it would be 10 at 3 meters, 10 at 5 meters. Much more efficient than repeating 5 times as a dimension. Okay, so we have horizontal dimensions. We have a vertical dimension here, 4 meters. We have 2 loads. The horizontal load at pin C, we're loading only at pins, KN, and we have a vertical load here, E, 15 KN. Here. First step, all 4 reactions. And we know how to solve for reactions. Sum of moments about A, you get D sub Y, and D sub Y is 12.2 Kn. What I can do if I want to is I can sum forces in the Y, and I get A sub Y is 4.78. A sub X would be 5 almost by inspection. We got one force, 5 in the positive X direction. I saw that, so I have AX going in the negative direction, so that's 5. Okay. I'll tell you this too, there's a check, and you should always do this check. If you get, this is the first step, if you get your reactions wrong, everything you do, I mean, if you want a long truss and spend 30 minutes on it and your reactions are wrong, everything's wrong. So on an exam, I can't go back and check it, see that you did the right calculations with the wrong number. It's impossible. So I would always advise you to check. That's how you check it. The forces here, get D sub Y, some forces in the Y, get A sub Y. Take moments about D, you should get A sub Y, same A sub Y that you got before. Or you can take moments about A, D sub Y, take moments about D, A sub Y. Your check question is sum of forces in the Y equal to 0. You always have a check. I told you, I don't know, a week or two ago, all the problems had checks. This is one that's so important. I've seen students not do this and they make a math mistake or something here or leave out a course and they're wrong and they work on the truss for 20 minutes and everything's wrong after that. So make sure reactions are correct. Okay. Go through the solution. Let's start pin A. By the way, let me show you the way these trusses are typically labeled. This left reaction is A, and we're going around here in a clockwise direction. It also depends on how the problem is labeled in the book, but typically this is how you do it. This is B, this is C, E, E, and F. Okay? That's the labeling. We'll go around clockwise. Let's start at pin A. Got forces, and then members that are unknown. So this is a particle problem. Very simple. Here's the y component, and here's the x component. I'm going to assume the unknown forces in the truss are tension. So here's AE, here's AB. Please use slopes, don't use angles. Trusses are typically dimensioned. It's 3 horizontal, 4 vertical. This is a simple 3, 4, 5 triangle. Okay, so I put that on there, 3, 4, 5 triangle. Some forces in the y, 0.78 plus 4/5 AB. It. You got AB is equal to minus 3.48 kilonewtons, which means choosing tension everything, which we know now this negative sign means it's compression. So I'm going to write this as AB is equal to 3.48 kilonewtons compression. So let me do, I'm going to do something real quick here because show this as tension. I'll go to the next joint, which is going to be pin B up here. And so this force in here occurs also at pin B. It's 3.48 dB. And so as we draw this pin, look at this, the tendency is to look at this, say, oh, that's, that's tension. So tension is always away from the joint. Compression is always into the joint. Tension is always away from the joint. Compression is always into the joint. So I have this as tension, and I draw this as tension. If it's not tension, it's compression. So from this point on, the rest of the truss is incorrect, because you're going to treat this as a positive y and a positive x. Compression. But you have to keep track of this, and here's how I would recommend you do it. I'm not going to erase this, because this is how I solve this problem. Okay, I'm going to leave it like it is. I'm going to take a red pen, and I'm going to put the arrow down here. When I see this red, if I'm looking at this diagram, it tells me immediately it's compression. I don't have to look at it. Okay, it's compression. So when I draw, go to pin B, I draw this as a compression member. And then I draw BC as tension and BF tension. So I have B, BC, okay, BC. So here's pin B. I know this value. Again, simple. Some forces in the X, either way, doesn't matter how you start it by. Some forces in the X. Then I have BC, that shows the tension, and then the X component is 3/5 3.48. Again, this is compression here. The component is in the positive x direction. Compression and tension doesn't matter plus or minus, it's the direction. And so it's positive. So BC is equal to minus 2.08 kilonewtons. Because it has tension, compression. I'll put this arrow down here. So it tells me it's actually compression, and then I write this as compression. As you're solving, I want you to put the answers here. So here is the answer for AB. This is C, and so I'll write the answers in here as I'm going. Pin B, I'm going to go to pin E next. Pin F. So pin F up here is the next one in line. B, F, I'm going to go down to F. I want to go over here. There's too much going on that I don't know. So I'm going to go down to logic on how you do this. So pin F, we have 1, 2, 3 forces, 2 unknowns. Won't have more than 2 unknowns. Just use some forces in the X and some forces in the Y. So here is pin F. This is 7.08, which we solve for. P we choose as 2.78 tension found. And then C we're showing as tension, 3.45 slope. Some forces in the Y, 7.8 kilonewtons. And choosing tension, this is also positive. So vertical is Y is 4/5 of FC equals 0. So FC also comes out to be negative 0.48 kilonewtons. Again, I draw the red, indicate its compression. I'll label that back on the truss that we're looking at. So there's pin F. We go to pin E. So pin F, then we're going to go to pin E, and this one's easy. Do this by inspection. Okay, so we go to pin E. 9.17 kilonewtons. D. 1.5 kilonewtons tension. 15 down where it is. So this, of course, is no Y. This has to, EC has to be 15 tension. This is 9.17 kilonewtons tension. ED has to be 9.17 kilonewtons tension. You can write force X and equals 0, Y equals 0. The answers I know you know. Okay. This force has to equal this force. This force has to equal this force. Again, you write it up there. So what we're left with is this last number here, CD. I'm going to go to C. And you might ask, well, why don't you go to D? You've got 2 forces. You can do that. Do that. We'll call that in probably 30 seconds. You've got in the Y direction and this, and forces, some forces in Y, solve that, and some forces in the X. I'm going to go to E, out here to D instead of down here to D. And so we have 1, 2, 3, 4, 5. This is pin C. Got the force is 2.08. There's the 5 kN applied force. This is 3.48, and it was compression, 0.5 tension. And again, I want to CD, 4.5 slope, got that as tension. And again, I'm going to just some forces in the X, 5, 2.08, plus the 3/5, 0.48, CD equals 0. It's not hard, again, you're adding. CD is 15.3 kilonewtons compression, and done. The check, as we checked the actions, I would advise you, well, this would be really disappointing if it didn't check, but you need to know, and you can tell that you've done this correctly, sure, on this check. Or at the beginning, just before we did this point, what we needed was this force, and I said, we're going to go to C, but you could go to D. It's only forces, or one force, two forces, the Y, and then this D, and known as CD. You go here, solve it, and instead of, in addition to here, should get the same answer. And if you get the same answer, you have done the entire truss correctly. Okay, at least your math is correct. You kept track of tension or compression, you didn't miss it up. If I went here first, and I got this, I don't know if you recognize this or not, but you could go to here for a check. But I'm going to suspect if you did this, maybe a minute, wouldn't go here to do all of this, solve this as a check from a time factor. So I did this. My answer in my check took me a minute to do that. You have a check. The last member that you do out here, work this joint here and solve, and it should come out to be 15.3 newtons compression. So that's an example. We'll go back. And we might do this again a little bit. There's something else I want to skip from my first page. This is the concept of a zero force member. By inspection, you can tell if there's a member in there that does not have any force at all. It's zero, and it's primarily there for stability and maybe to prevent a little deflection or something. It's going to carry no load. Look at this simple truss here. Remember BD, there's a force up here. Look at this joint here. Okay, I'll have a X component F, so there'll be force E. There'll be a force DC, and here's DB. Some forces in the Y, I have DB, but I don't have any value for that. Some forces, the Y equal to 0, DB has to be equal to 0. Some forces in the Y, equilibrium. This is in an equilibrium if DB has a value. I call this a T intersection, and anytime you see a T intersection, you'll see that there won't be a Y component. Be X depending on how it's oriented, but usually it's a Y component. So we some forces in Y, there's nothing here, DB has to be equal to 0. Another one that's at an angle, call this sort of a quasi E intersection. Be a Y component with this force. Again, if I sum forces in the Y, it would be this Y component equal to 0 because there is no Y force. So if you see this, something like this at an angle, force here, that member has to be equal to 0. Let me show you this one. Here's a rectangular truss, two diagonals. I have a force out here at D. This is A, this is B. I'm gonna look at pin B. Force here, another force, put it both as tension, doesn't matter. Force in each direction. Some forces in the X direction. I have this force. Nothing in the X direction here. This has to be equal to 0. The forces in the Y. Force in the member. There's no other force in the Y direction. Member has to be equal to 0. What I would do, if this was a problem I'm working on an exam, 0 here and 0 here, no explanation needed. What I do is show it as 0. And when you solve this truss, you just simply ignore these. Don't even put them in. I mean, they're not going to be anything. They're 0. So you've eliminated these already. If they're not 0, of course, that's wrong. I mean, you got to make sure to do it. And we'll do some more problems and identify 0 load members. But this ends up being really efficient sometimes because sometimes you can eliminate a lot of trusses members with the 0 designation. Okay. Nice weekend. And continue on here with a couple of examples of trusses using the method joints, and then we'll use a second method called the method of sections to truss trusses, and we'll show that next week.